is Zhengyu-Wu, and I'm the second-year PhD student from Imperial College London, United Kingdom. It's a great pleasure to be here to present our latest work on development of a simulation system, as well as a novel synthetic data set. It's also a video data set, the first video data set here in the industry, and that is generated from computer. We do this for enhancing computer vision in construction site safety. Just to give you a brief background of my research, we all know that construction sites are one of the most dangerous places to work with. According to the Health and Safety Executive in the United Kingdom, last year we have 51 fatal injuries. And we've seen the number growing since post-COVID because we have more and more people getting back to work. With the advancement of computer vision, its application in safety monitoring is increasingly crucial because we can use this technology to do some early warning and to predict the unsafe behavior from happening. We've seen some examples here from the literature, such as PPE compliance check, machinery detection, worker detection tracking, and also intrusion detection. In our research, we've identified a few research gaps presented in the current field. First of all, as you all know, that deep learning methods often relies on extensive data collection and the manual labeling, and this can be a really time-consuming process, and sometimes it is also prone to error. Currently, we have two big data sets in the field, which is MOCS and ACID, but they only contain images. And that means most of the study based on this data set will be limited to low-level tasks like object detection and tracking, and that further restricts us from exploring some high-level tasks from things understanding that often needs spatial temporal feature extracted from videos. So the reason why we are doing a synthetic data set here is that a synthetic data set can be a promising solution to the gap here, because we can, in theory, generate as many data as we want. And however, they actually suffers from the domain gap, which is the biggest challenge in synthetic data. And as you can see the example here, they just lack realism. And that means the model trained on this data will perform poorly in real-world applications, because in real world, we will see the video from cameras as are much more complicated than these generated from game engines. So the contribution of our study are basically twofold. First of all, we create a simulation system which simulates realistic vehicle dynamics and also accurate worker behaviors. We also adapt domain randomization to further improve the realism of the data set. We do this by randomizing the weather and the lighting condition to further minimize the domain gap I just mentioned. And secondly, we propose the first photorealistic synthetic video data set in the industry. It provides a continuous image sequence with precise labels that is able to support common tasks like 2D and 3D object detection, tracking, and instance segmentation. But it also enables other additional tasks like depth estimation, action recognition, and the behavior analysis. So this is the overall framework of our method. I know there's a lot of information here, but you can see it as two parts. So on the left, we have the construction simulation system, and on the right, we have the data set generated from the system. So let me show you, if I can move to sorry. So on the top here, we start with the generation of a digital twin model by merging a photogrammetry model that captured from the site with the Google Earth map. So the photogrammetry model will provide accurate representation of the site up to date, but we also use the Google map to provide us the surroundings so we can have unlimited distance of view into the model. And we also use the site logistic plan to help us generate the vector map, which was later used for traffic simulation. We then pick up some random points around the vector map and spawn some of the cameras and different types of agents, such as workers and vehicles. Since we are doing a simulation here, we are also able to change the time of the day and the weather free of charge. So that is the formation of the simulation system. And on the right part, you will see that we use Unreal Engine, which is kind of the state-of-the-art rendering system that we use it to render the simulation into videos. We get the image sequence, and then we also labeled automatically the positions and orientations of these objects with the 3D bounding box, as well as some useful mask annotations, such as the instance segmentation here. Yeah. So here are just examples of this data set. So you can see they are all videos. The data set includes RGB images, depth information, normal maps, and segmentation. I hope you can see from the video how realistic these data are compared to the previous work. And I hope this useful annotation will be able to enable more high-level tasks that has not been well explored in the field. So to validate the usefulness of our dataset, we conducted a few experiments. And the model we choose is ULV8, which is a popular one-stage anchor-free model that has been used a lot in the study. And the training details is as follows. So we trained the model on two different data sets. One is the real data, which comes from a combination of two popular public data sets, MOCS and ACID. I would say the difficulty of data set is normal, but then we have another data set, is the synthetic data set, which we just generated from the simulation. So the difficulty of this data set will be harder because you can tell from the images and the lighting condition and the weather condition is making a lot of barrier for the model to detect these objects. Notably, we also have a third data set, but only for validation. And that's the data set we captured from a case study construction site. It contains a top 100 most unique images. And that's for validation only. So the model trained on the previous two data sets will never seen this model during their training, never seen this data set during their training. And here are the results. So first we trained and tested the models on the respective data set, and they showed strong performance in their own domain. And that means this model have learned pretty well in their own domain. And then we start to switch the validation data set. So now the model trained on real data set is actually validated on synthetic data set. And you can see there's a sharp decline in the performance here. And this is due to the domain gaps between the two data sets. And it highlights how significant this domain gap can reduce the performance of a pre-trained model when they are being applied to a real-world scenario. So to explore how synthetic dataset can help mitigate the problem, we tested the model on a previously unseen third dataset called the case study dataset. So we trained another model using a combination of real and synthetic data, and actually the model trained solely on the synthetic dataset has outperformed the baseline model by 20% in the performance of detecting the dump track. And impressively, the model trained on the combination of the both datasets demonstrated a better performance with a substantial 30% improvement in detecting the dump track, as well as a 13% increment in detecting all the classes. So that means with the help of synthetic dataset, we are able to improve the robustness of the model, and they can be generalized to be applied in different construction sites. So based on the previous finding, we are also curious to know, although we cannot fully eliminate the need for a real data, to what extent can we use the synthetic data set to help us reduce the need for this real data? So we conducted an experiment by combining a subset from the real data with the entire synthetic data set. So there are two diagrams, and on the top is the one we validated on real data, and on the bottom is the one we validated on the case study dataset. So you can see a similar pattern here, and you may notice a breakpoint at around 25%. That means we can reduce the number of real data here up to 50% and still get a comparable performance in the model. And with more real data, the model gets better, and the performance of the synthetic data is actually outperform the baseline model with more data, more than 25%. So that means synthetic data can not only help us reduce the dependence on real data, but it can also help the model perform better in scenarios it hasn't seen before. And in conclusion, our research has made several important contributions. We developed the first synthetic data sets in the construction industry, featuring photorealistic images and accurate labels. Our finding shows that while synthetic data set cannot eliminate the need for real data, it can significantly reduce the dependency on manually collected and annotated real data. And this will not only help us save time and resources, but also help deal with the privacy issue and data quality issues. It improves the model robustness and accuracy, particularly in unseen scenarios, such as with adverse lighting and weather conditions. We also provide valuable annotations for more advanced tasks in the field, so hopefully we can see more tasks using this data set in the future. Looking ahead, we plan to expand the ConSynth data set to include more category of the construction equipment. For now, we only have worker and 2 different kind of trunks. We also want to explore more on the small object detection, because currently the model performed pretty poorly on detecting the workers in adverse weather and lighting condition. I'd like to take this opportunity to thank my supervisors for providing the invaluable insights, and also our industrial collaborator for providing the resources necessary for this study. And thank you very much for listening. I want to open the floor to questions.